Differential equations arise across many disciplines. To get an idea of a differential equation, let's see an example. Here, we have a tank of water. When a solid is dropped into the water, it goes down to the bottom with some acceleration. Let's find a way to describe the acceleration of the solid in the water mathematically, as shown here. Suppose the body is moving with speed v. Then the acceleration of this body is given by dv divided by dt. The solid is a free-falling body without any external force, so the acceleration is equal to the acceleration due to gravity. This is denoted by g. However, there is a variation in the velocity due to the resistance force by the water. This change in velocity per unit time is equal to minus kv. This term is due to the buoyant force by the water, where k is a constant. The minus sign signifies deceleration. This means that the equation of motion for the acceleration of the body, dv upon dt, is g minus kv. This looks like a polynomial equation in dv divided by dt. However, the equation is in derivatives, so we can call this a differential equation. This differential equation signifies the equation of motion for acceleration for the body and belongs to the category of ordinary differential equations, since we have only one variable, v, here. Some examples of differential equations are shown here. Formally saying an equation involving a derivative of a dependent variable with respect to the independent variable is called a differential equation. In the differential equation for the acceleration of the body in water, the variable v is the independent variable. The variable v is the dependent variable. For convenience, we express derivatives with the convention shown. The first derivative of y with respect to x is denoted by y dash. The second derivative of y with respect to x is denoted by y double dash. The third derivative of y with respect to x is denoted by y triple dash. For higher order derivatives, to avoid so many dashes, we use the notation shown. The nth order of a derivative is denoted by y subscript n. There exist many types of differential equations. However, we can classify them based on some of their characteristics. While classifying a differential equation, we first find its order and then its degree. To find the degree, verify whether the differential equation is a polynomial differential equation. The first three differential equations are polynomial differential equations in different order derivatives. In the fourth and fifth equations, even though there are derivatives, there is a trigonometric function of the derivative. So these are not polynomial differential equations and therefore their degree cannot be found. The order and the degree of only polynomial equations can be determined. Consider the second differential equation. The derivative with the highest order signifies the order of the differential equation. If we look at the order of the derivatives, the highest derivative among the derivatives is 3. This signifies the order of the differential equation. Therefore, the order of the differential equation is 3. Hence, the order of the highest order derivative occurring in a differential equation is called the order of the differential equation. Now that we have determined the order, we will see how we determine the degree of the differential equation. The degree of the polynomial differential equation is the degree of the highest order derivative of the differential equation. Here, for the order of the derivative 3, the degree is 2. Therefore, the degree of the differential equation is 2. Now, we can term this equation as a third order, second degree equation. If you observe carefully, the degree of the second order derivative is 3, but we considered the degree of the highest order only. Consider another differential equation. This is not a polynomial differential equation. Hence, its degree cannot be determined. The order and degree of other differential equations are shown here. The order of the first equation is 1 and its degree is 2. The order of the second equation is 3 and its degree is 2. The order of the third equation is 1 and its degree is also 1. Please note that the order and the degree of a differential equation are always positive integers. As you have seen in the previous module, differential equations arise from different situations. Once we arrive at a differential equation, we need to find its solution. Let's see what the solution for a differential equation is all about. Consider the differential equation dy upon dx is equal to e power x minus 4. We claim that function y is equal to e power x minus 4x plus 3 is the solution of the differential equation. Let's begin by differentiating both the sides of this equation by x. On the left-hand side, we get dy upon dx, and on the right-hand side we get e power x minus 4 plus 0. Or dy upon dx is equal to e power x minus 4. Observe that this is the same differential equation that we considered earlier. This means that function y satisfies the differential equation, and a function that satisfies a differential equation is its solution. Therefore, the function y is the solution of the differential equation. This proves our claim. There exists two types of solutions of a differential equation: a general solution and a particular solution. To understand these two kinds of solutions, let's consider the same differential equation. The solution that we considered for this differential equation is a function y as shown. Suppose function y is of the forms as shown. Each of the three forms of the function y entitles to be the solution of the differential equation, since their derivatives are the same. We can represent the constant in the equations with a letter. We choose c here. So this function represents all the solutions of the differential equation. Such a function is called the general solution. And the function obtained by replacing the value of c by a number is called the particular solution. Given a general solution, let's learn to build a differential equation out of it. Let's assume that the function x into y is equal to ax square plus b upon x is the general solution of a differential equation. Let's find the differential equation. Observe the equation carefully. Note that the variables in the equation are x and y, and the constants are a and b. To find the differential equation, keep on differentiating the general function till the constants get eliminated. Let's begin by multiplying both the sides of the equation by x. The equation takes the form x square into y is equal to ax cube plus b. Now, let's differentiate both the sides of this equation so that b gets eliminated. Applying the product rule on the left, we get x square into dy upon dx plus 2xy is equal to 3ax square plus 0. Now, dividing both the sides by x, we get x into dy upon dx plus 2y is equal to 3ax. Let this be equation 1. Again, differentiating both the sides by x, we get x into d square y upon dx square plus 3 into dy upon dx is equal to 3a. Let us denote this equation by 2. On substituting the value of 3a from equation 2 in equation 1, we get the expression as shown here. Now, simplifying this equation, we get x square into d square y upon dx square plus 2x into dy upon dx minus 2y is equal to 0. This is the required differential equation. Based on this discussion, we can devise some rules to form a differential equation. First, observe the number of arbitrary constants present in the given general solution. Then, find the derivative up to the order based on the number of constants. For example, if the number of arbitrary constants in the general solution is 1, then differentiate the general solution once. Similarly, if the number of arbitrary constants is 2, then differentiate the general solution twice. Finally, eliminate the arbitrary constants using the equations obtained. An example is shown here. Differential equations are used to depict some geometrical properties of curves. For example, the differential equation x plus y into dy upon dx is equal to 0 represents a family of concentric circles with the center at the origin. Let's see how this differential equation was obtained. We will begin with the equation of a circle whose center is at the origin. Here, the variables are x and y, and the constant is r. On differentiating this equation of a circle, we get 2x plus 2y into dy upon dx is equal to 0. Observe that the constant is eliminated. This can be written as x into dx is equal to minus of y into dy. The question is, How does the given differential equation represent a family of circles? Let's integrate this equation as shown here. This gives x squared upon 2 is equal to minus of y squared upon 2 plus c1. This implies x squared is equal to minus of y squared plus 2c1. Or x squared plus y squared is equal to c, where c is equal to 2c1. Observe that the constant on the right-hand side can assume any value among real numbers. Therefore, we can assume countless number of circles. These circles are called a family of circles. Next, let us try to find the differential equation that represents a family of parabolas oriented along the y-axis and with a vertex at the origin. To achieve this, we will first take the general equation of a parabola with its vertex at the origin and direct it towards the positive y-axis. Here the variables are x and y, and the constant is a. We will form the differential equation in such a way that the constant a is eliminated. So, differentiating both the sides of the equation with respect to x, we get 2x is equal to 4a into dy upon dx. Rearrange the terms in the equation as shown. Now, substituting the value of 4a in equation 1, we get x squared into dy upon dx is equal to 2xy. On dividing both the sides of the equation by x, we get the differential equation that represents the family of parabolas. Let's see how this differential equation represents a family of parabolas. The differential equation can be rearranged as shown. Now, integrating both the sides, we get log y is equal to 2 log x plus log c. This implies that log y is equal to log x squared plus log c. Or log y is equal to log of x squared into c. Now taking anti-log on both the sides, we get y is equal to c into x squared. This can also be represented as shown. Here d is the reciprocal of c and belongs to the set of real numbers. You will notice that this equation resembles equation 1. So the family of parabolas with variations in d is as shown. Let's summarize the procedure that we have seen. First, we will deal with differential equations with one constant. The equation representing a family of curves with one unknown parameter is as shown. Here a is the unknown parameter. First, differentiate equation 1 to obtain the equation shown. Next, eliminate the unknown parameter from equations 1 and 2 to obtain the differential equation here, indicated as equation 3. Observe that the differential equation obtained does not contain unknown parameter a and contains the derivative. Now, let us see how to form a differential equation that represents a family of curves with two unknown parameters. Let's take an equation as shown. Here, a and b are the unknown parameters. First, differentiate equation 1 to obtain equation 2. Since there are two unknown parameters, a and b, two equations, 1 and 2, are not sufficient to eliminate them. Therefore, we differentiate equation 2 again to obtain equation 3. The required differential equation is obtained by eliminating the unknown parameters using equations 1, 2, and 3. Note that the number of unknown parameters determines the order of the differential equation. If the number of unknown parameters present in the equation corresponding to the family of curves is 2, then the order of the differential equation obtained is 2. Till now, you have seen how to form a differential equation from a given solution. Now you will see how to find the solution of a differential equation. In this lesson, you will explore a method to solve first-order, first-degree differential equations. Consider the differential equation dy upon dx is equal to f of x, y. If f of x, y can be split into two functions, then the variable separable method is applied. Otherwise, we go for another method, which is, however, beyond the scope of this lesson. Let's now understand how to solve a differential equation with the variable separable method. Consider the differential equation dy upon dx is equal to 1 plus y square whole divided by 1 plus x into xy. Observe that the right-hand side of the differential equation can be expressed as the product of two functions, where the first function is a function of x and the other one is a function of y. Here, the right-hand side is expressed as functions of x and y, so that the variable's separable method can be applied. Rearrange the equation by bringing the function of y on one side and the function of x on the other, as shown. Now, the expression 1 divided by 1 plus x into x on the right-hand side can be written as 1 divided by x minus 1 divided by 1 plus x. Finally, integrating both the sides, we get half log of 1 plus y square is equal to log x minus log of 1 plus x plus log c. On further simplification, we get 1 plus y square into 1 plus x whole square is equal to cx square, which is the solution of the given differential equation. We often come across functions as shown here. There's an interesting property of such type of functions. Let's pass these functions through a test to know the property. Substitute kx in place of x and ky in place of y. Here, k is a constant. Observe that in both the cases, the constant k with non-negative integral power can be taken common without disturbing the expression. Such types of functions are known as homogeneous functions. Here, the function f of x, y is of degree 2, and the function g of x, y is of degree 0. Any homogeneous function can be expressed as shown. Here, n is the degree of the homogeneous function. For example, if we consider the first function, we can represent it as shown. We can say that this is a homogeneous function of degree 2. Similarly, g of x comma y can also be written as y raised to the power 0 into g1 of x upon y. Here, 0 is the degree of the function g of x comma y. Now, we define a homogeneous differential equation. A differential equation of the form dy upon dx is equal to f of x comma y is said to be homogeneous if f of x comma y is a homogeneous function of degree 0. Given a homogeneous differential equation, we can convert it into a form that can be solved using the variables separable method. Let's see how. Consider a homogeneous differential equation of degree 0. Let's substitute y is equal to vx. On differentiating this expression, we get dy upon dx is equal to v plus x into dv upon dx. Therefore, equation 1 can be written as shown. Now, a differential equation in this form can be solved using the variables separable method. Let's see how. Rearrange the equation by bringing the functions of v on one side and the functions of x on the other side, as shown here. Now that the variables have been separated, we can perform the integration easily. Once the solution is obtained, we can replace v with y upon x. It has to be noted that if the homogeneous function in the differential equation is of the form h of x by y, then we solve the differential equation by substituting x is equal to vy. Let's solve the differential equation shown. First, we will have to find whether this is a homogeneous differential equation. Let's check that out. Since the function on the right-hand side of the equation is a homogeneous function of degree 0, we can say that this is a homogeneous differential equation. Let us now substitute vx in place of y. Also, we will substitute the derivative dy upon dx. We get this expression. Simplify this equation and rearranging the equation by bringing the functions of v on the left-hand side and the functions of x on the other side, as shown. Now, the equation is in variable separable form. We will further simplify the equation as shown. Finally, integrating both the sides of the equation, we get this equation. On simplifying the expression, we get v upon v plus 1 whole square plus log vx plus x equals to log c. Now again, substituting v equal to y divided by x. Simplifying the equation, we get this. Solve it further to get the solution. We get the solution as 2xy upon x plus y whole square plus log of x plus y upon c is equal to 0. A linear differential equation is of the form dy upon dx plus p into y is equal to q. In this differential equation, P and Q are constants or functions of x. To find the solution of this type of an equation, first multiply both its sides by a function, say h of x. Denote this by equation 2. Choose the function h of x such that the right-hand side is a derivative of the product of y and h of x. Next, find the derivative of the product of y and h of x. The expression obtained is as shown. Now, cancel the common terms from both the sides. This gives p into h of x is equal to h dash x, or p is equal to h dash x divided by h of x. Now, integrate both the sides as shown. This gives h of x is equal to exponential raised to the power of integral of p with respect to x. Now, substitute the value of h of x in equation 2. The left-hand side can be represented as the derivative of y into exponential raised to the power of integral of p with respect to x. Rearrange the equation as shown. Now, integrate both the sides of the equation. The integral on the left-hand side vanishes. This is the required solution of the differential equation. Here, exponential raised to the power of integral of p dx is called the integrating factor. Therefore, the general solution of equations of type 1 can be obtained by the formula y into the integrating factor is equal to integral of q into the integrating factor with respect to x. If x is replaced by y and y is replaced by x in equation 1, then the linear differential equation obtained is as shown. Its solution is given by x into the integrating factor is equal to integral of q into the integrating factor with respect to y. Consider an example of a linear differential equation. Compare this equation with the standard equation. Here, p of x is equal to 1 upon x and q of x is equal to exponential raised to the power of 1 plus x square. First, let's evaluate the integrating factor. This is equal to exponential raised to the power of log x or x. Now, substitute the values of q of x and the integrating factor in the solution of a standard equation. This gives x into y is equal to integral of x into exponential raised to the power of 1 plus x square with respect to x. Let's denote the right-hand side by I. Assume 1 plus x square is equal to t. This implies that 2x dx is equal to dt, or x into dx is equal to dt upon 2. Now, the integral reduces to half into integral of exponential raised to the power of t with respect to t. This implies that I is equal to half into exponential raised to the power of t. Substituting t is equal to 1 plus x square, we get the value of I. Now, substituting the value of I in equation 1, we get x into y is equal to half into exponential raised to the power of 1 plus x square plus c